Oh, thank you. Thank you for inviting me for this Solar Orbiter webinar. And yeah, as Miho already said, we are exploring the solar corona with Solar Orbiter, and in particular through the Metis-led Solar Orbiter observing plants that I will show you soon. So the presentation is with all the Metis team and collaborators. So all the research that you will see today are of course not only mine. So the outline of the talk, I will present you the Metis instruments if you are not familiar with it. Then the observations, how we made the observations, the science objectives of the Solar Orbiter mission, and how they are studied by Metis and Solar Orbiter observing plants. And then I will present you some science highlights and some work in progress that is done now, and of course what's next. So the Metis is the coronagraph on board Solar Orbiter and is an externally occulted coronagraph, and he provides the imaging of the extended corona. So from it has a field of view that at 0.28 AU is going from 1.7 to 3 solar radii. Of course, the field of view is changing while we are approaching the sun, and while Solar Orbiter is moving along its orbit. And this designed with 2 channels, so observations are possible in the visible light, in the polarized visible light, and in the range of 580 to 640 nanometers, and also in the UV. And the line that we are observing in is the hydrogen Lyman alpha line. And since we have these two channels, we can investigate the density distribution of the coronal electrons, but also of the protons. And then the 2D solar wind outflows, we can have estimation of the velocity of the expansion of the corona, and also we can investigate solar transient and study the dynamics of the plasma in coronal mass ejection in CMEs, and not only these CMEs. One of the main study of Metis is the study, as I already said, of the solar wind outflow, so the velocity of the expansion of the corona. Since Metis is really observing in the regions when the solar wind undergoes acceleration from the almost 100 kilometers per second to near its asymptotic value, and we can do it observing how the Lyman alpha emission is dimmed by the coronal expansion, and then compare this dimming with the model, with what it is expecting for the Lyman alpha to be in a static corona. And so we can from these observations and these measurements, applying what is called the Doppler dimming technique, then we can calculate the outflow speed. And of course, this is based on several physical and geometrical parameters that you see listed here. And the results are already there are different papers about it, and one paper is under revision, so it will come out hopefully soon. Then the Metis achieves really high spatial and temporal resolution that were never obtained by other coronagraphs. So this allows us also to have observation in some observation that we could never have before. So for the spatial resolution, we have for the visible light around 2 pixels, for the UV a bit more, 4 to 7 pixels, and the temporal resolution is very high. In UV, we are higher than 1 second resolution. In the visible light, depending on which kind of acquisition scheme we are using. Here is a table that resumes what I'm saying. So we can acquire in polarized brightness, and so we are in around 60 seconds, then in the total brightness acquisition, and we have 20 seconds, and then we can even go to 1 second for fixed polarization. For the UV analog, yeah, as I said, we are around 1 second, about 1 second. So Metis is not observing always, because it has the observations are limited as for the whole solar orbiter remote sensing instruments by the telemetry. But we also have another limitation, since when the spacecraft is off pointing, then Metis, the heat shield door, needs to be closed. Otherwise, we can have problems with the light from the sun disk entering directly on the detector. So this can make problems for the instruments. So the observations are anyway during the remote sensing windows. There are usually 3 days per orbit. One orbit is around 6 months. But the rest of the time we are in synoptic mode, so we have reduced cadence and resolution, but still we can guarantee observations. And then we also have some target of opportunities that usually are outside the remote sensing windows to observe stars for the calibrations, and also joint observation with other assets like quadrature with other instruments. This is just a table when you see all the observation that Metis was doing, and you can find it also in our website. That is here at the top, from the 2020 till today. So we are more or less here. And you can see that most of the observation is around the remote sensing windows, while we can guarantee synoptics, sometimes only in the BR range. But now, I mean, the idea is to have also the UV for as much as possible, also outside the remote sensing windows. Here are listed the solar orbiter top level questions on the left. So they regard in particular the solar wind, so to understand the solar wind, the transients, and then the particles, so how do solar eruptions produce the energetic particles, and then the connections between the sun and the heliosphere. And on the right you have for each solar orbiter question how Metis can contribute to answer these questions. And all the solar orbiter top level questions have different sub-objectives, and these sub-objectives are answered by what we call SUPs, that are the solar orbiter observing plans, and is a set of common operations from multiple instruments addressing several mission sub-objectives. So here is a list of the SUPs that are Metis-led, and I will go into detail soon. So the first 5 are already producing results, or at least we have run them for since many orbits. So we have observation from it. The last 3 are just new, or we are still obtaining the observation from them. And here also I listed which objective are answering these SUPs. To go into the details. The first one is the probe quadrature, and is designed to acquire observation above the limb of the source region of the solar wind plasma by Metis that will be later sampled in situ by Parker Solar Probe. So they happen when we are in quadrature with the Parker Solar Probe, and when during its perihelion. Then we have the boundary expansion, and this SUPS was designed directly to answer the question, does low wind originate from the over-expanding edges of coronal holes? And I'm also listening some cadence of the observation, but usually they are done with the high spatial and temporal cadence observation. This is what we need to answer the objectives of solar orbiter. Then the coronal dynamics, that it aims at observing structure in the outer corona and linking them to the heliosphere observed from the in situ, but it can use also the higher latitudes to scanning the outer corona and looking for features like pseudostreamers and equatorial coronal hole, or during a perihelia, since there is a reduction of the dependence on the solar orbiter rotation, to study the temporal evolution of coronal structure. Then the density fluctuation, it aims to study density fluctuation in the extended corona. And also we have the eruption watch, that is a full disk high resolution plan designed to catch eruptive events. Of course, it tries to address all the science around coronal mass ejection, but also the ambient corona. And it aims to do it at very high temporal resolution. So some highlights from the SUPS I just mentioned. This is the results that we had in the paper of Telloni et al. 2021, and this is the real first the first solar orbiter PSP quadrature that happened in the 18th of January 2021. And so this was actually the first attempt to explore the evolution of solar wind from its source on the extending corona by Metis to the inner heliosphere by Parker Solar Probe. So we were able, in this paper, the authors were able to connect actually what was coming from, what was seen from Metis and what was measured at Parker Solar Probe, and they were measuring the flow aligned magnetic field and the bulk kinetic energy flux density, in particular giving an estimation of the half-band radius at 8.7 solar radii. Then we also have some results about the coronal heating rate in the slow solar wind. So in the expanding corona, this is again the first time we can do something like this. Here is the configuration of this is an observation from Metis, the 1st of June 2022, and here where the two spacecraft were, and particular Parker Solar Probe was here. So we had an estimate of coronal parameters from 6.3 to 13.3 solar radii, and we were able to do it using a 1D model conservation of mass and magnetic flux and constraint from PSP, and then the heating rate was empirically estimated solving the propagation equation of Alphen with some kind of approximation. Then we go to the Metis high cadence observations, and as I show you on the right video, on the right movie, you can see the total brightness in the first video. Then you see the base difference images, and then the running differences. Sorry. So the really key point about this high cadence observation are that we can reach a really high temporal resolution. There is at least a factor 5 or even more order of magnitudes more higher than existing coronagraphs. Then the spatial resolution, when we are around 0.3 AU, so at perihelia, we can reach resolution as low as 2000 kilometers per pixel. And the signal to noise also is very high. And the duration, we have a lot of constraints, but the length of duration, it can be very long. And of course, we have the UV channel that is completing our observation, and this is, of course, the first time. So some results related to the high cadence observation. There is a paper from Andretta et al. That is under revision. It was submitted, and he is able to see some waves or density oscillation in the corona. And here are the main properties of these oscillations. And the author infers that maybe there can be leakage of P modes into the corona, but this is still under discussion in the paper. Then we have this result that just came out from Paolo Romano in APJ, and he was seeing this outward propagating helical structure that it extends up to 3 solar radii. That appeared after a large pseudo-streamer eruption. So this is the relaxing phase, and this is again the total brightness of Metis with a very high cadence, 20 seconds. And here the base difference and the running difference. So this helical structure persisted for more than 3 hours, and here are the results. So they made a comparative analysis with the high resolution MHD simulation of bursty interchange reconnection, and they found similarities on what they see in the observation. So they interpret this helical structure as a consequence of twist and plasma liberated by interchange reconnection. Then another result from the coronal hole boundaries soup. This is impressed in solar physics and is from Gampupun. And here they were analyzing the solar wind outflows from 2 different structures, open field corridor and a mid-latitude coronal hole, and they were observing it also with the Metis, but also with the eyes on Hinodi. And what they found is a difference between the plasma corresponding to that can be related with the 2 structures. So they find that in the open field corridor there is higher electron density and lower outflow velocity, and then they found these results in the middle corona. Even though the plasma properties in the low corona were found relatively similar, and then also the speed of the solar wind from the open field corridor shows no correlation with the magnetic field expansion factor, and this may suggest that other mechanisms like reconnection can play an important role in driving solar wind variability at that height. Then we go to solar transient. We observed with the high spatial and temporal resolution different CMEs and events in the corona, and so Metis is able to identify the mechanism that are driving the eruptions. The main see the sources of the flux injection into the Earth-sphere to check if they reside in the corona, and study the restructuring of the global solar atmosphere after a CME. Here we have some examples. I listed here the paper that are already published or they are in preparation. And then I also would like to show you some work that is done at the moment on two events that we saw in the last eruption watch campaigns. This is related to the 14th of March 2024. Here we see a filament eruption in the EUI instruments. You really see this huge filament that is erupting. And here on the right, I made a composite of EUI plus the two Metis channel. So you can see that after the eruption, you first see the front of the CME entering the visible light channel, there is the red one. And then you see the prominence, the filament that erupted entering the UV field of view. So here is really clear why, at least for CMEs, then also, of course, for other many things, it's so important to have the both channels to distinguish the structure that you are observing. And we also had FIP observing, even if it was only 6-hour cadence, but so the filament was here, so just lying above the an inversion polarity line, so just around two polarities, so we can study this filament also from the photosphere, the magnetic field in the photosphere. Here we started to make some GCS reconstruction of the front of the CME, and we were also able to reconstruct the velocity by high time plots, and we see that the velocity is around 400 kilometers per second and is comparable with one extrapolated by Cactus. So here we have to take in consideration that all the instruments are calculating the velocity on their plane of sky. Here is also some information on the filament eruption with the high time plots done in the EUI from EUI images, and we see that the velocity is around 320 kilometers per second, and of course we have to make also the Metis analysis when this prominence comes into the Metis field of view. Another event is this one. I need to go fast. So here we see, here it is the 21st of October, just to show you how we can really, I mean, these are observations at 1 minute cadence for 2 hours. And this is the event we are just studying, that we see first a CME, here is also 1 minute cadence when you see that it goes very slow. And then this CME on the west limb of the sun is perturbated by a halo CME that just comes into play. So what we are doing now is to study the halo CME. The big event is the Solo High team that is studying it because they see a really huge shock in their instruments, and we are of course helping them with this analysis with the Metis data. But the Metis team instead is working on the other CME and the interaction with the halo CME that we see on the west limb, also because we had EUI in coronographic mode, so we also have 3 temperatures in which we can observe the same events. So from the Metis UV and visible light channel, and then from FSI. I will go fast on this. We are also making some estimation of the geo-effectiveness of this CME, in particular the halo CME that we saw on the mostly on the east limb of the sun. Since we have a PhD student here in Naples, that's Priti Sahani, that is working on the geo-effectiveness of CMEs. So we are also working on space weather related activity, and I will be very, very fast on this. So we also contributed with the Metis to the May 2024 super solar storm that was observed, and maybe it's my, yes, sorry. And we, even if solar orbiter was not, I mean, it was on the other side of the sun, and it was in synoptic low SUP, mode. So we were observing with Metis every 2 hours and also Phi every 6 hours. So we were not really active on it, but still we showed that solar orbiter can contribute, and it was very important to have a spacecraft on the other side of the sun. Since here I made maps of Phi and HMI, but also EUI and AIA, and you can see that we could follow the active region responsible for the supersolar storm for 3 solar cycles, for 3 solar rotations. And this was possible to see the formation of the active region that was seen by solar orbiter, and also when the active region gave the highest energy flare. There is an X16 that was the 20th of May when the active region was on the other side of the sun. And also Metis is very useful for GCS reconstruction, since there is a work done by David Lario and myself, and we are working on some in situ observation during the main supersolar storm from Solar Orbiter and Parker Solar Probe. And Metis is very useful since we have another coronagraph looking at the event, because Metis was able to see all the events since we were really on the other side of the sun, almost 190 degrees. So I'm just going to the conclusion and future perspective. So Metis Solar Orbiter is going out of ecliptic. So of course, we will continue to contribute with SUPs that I listed, but also with new SUPs, contributing to study the longitudinal structure and distribution of propagating CME plasma and their geoeffectiveness, the longitudinal extent of coronal features and solar wind, exploring possible longitudinal patterns related to the magnetic field polarity. And here, just to conclude, is an example of a new SUP that is called pole-to-pole, that we can actually do now, because it needs a minimum inclination of 15 degrees. And here is what we are going to analyze, in particular the longitudinal distribution of coronal plasma at different helio latitudes. And I conclude with the Metis website, so feel free to go there and even to write us if you need something.